Targeted protein degradation. To attack kinase, we have seen the small molecule drugs which can affect the function of kinase. Another interesting idea is how about we break down the kinase itself physically? What does that mean? Well, kinase is an enzyme, and enzyme is a protein. Every protein in our body, if we need to break the protein, then first step is we add ubiquitin tag to the protein. And this step can generate multiple ubiquitin, the addition. Once the protein is added with the ubiquitins, then the proteasome machinery can recognize this ubiquitin oligomer, and then it just break down the target protein. It doesn't matter what is the protein, just they sense ubiquitin, and then if there is a ubiquitin, then the cargo protein can be degraded. And the ubiquitin can be recycled after the reactions. If you look at this machinery more closely, there are multi-steps of ubiquitin transferring system. The first carrier is the E1 protein, can bind to the ubiquitin, and then it transfers that ubiquitin to receiver E2, and E2 make a complex with the E3. E3 is the enzyme. E3 ligase transfers this ubiquitin finally to the target protein. Once this ubiquitin is transferred to the target protein, and this target protein is labeled with a death note, and it can be degraded by proteasome. So the issue is this target protein should be close enough to E3. To make it happen, if there is any molecule like this, one side bind to the target, the other side bind to the E3, then this molecule can be drug molecule which can physically destroy this target protein. Interesting idea, and this idea is called as a PROTAC, proteolysis targeting chimera. Here the chimera is these two molecule chimera, and proteolysis is the protein destruction by proteasome through this ubiquitination. Let's look at the full cycle of this reaction. So first step is E1 carries ubiquitin that transfers this ubiquitin to E2. Now this chimera molecule, this drug molecule, one side it binds to E3 ligase, the other side it binds to target. If this happens, then ubiquitin happens to the target protein, and this process can be repeated multiple times, which generate oligomers of ubiquitin here. Then this oligomer ubiquitin can be recognized by the enzyme proteasome, and proteasome break down this target protein. Very interestingly, after this reaction are finished, then ubiquitin is released and recycled. Also, this chimera molecule, after the job is done, chimera molecule also released, and then it can act again to make this whole cycle is catalytic. So the drug molecule, conventional drug molecules, once it binds to the kinase, it should stay with the kinase. But in this case, this drug molecule can be recycled. That means, in principle, with a very small amount of a drug, still we can achieve the destruction of a kinase. And here, the destruction is a physical destruction. It's a total removal of a target protein. To develop this type of a PROTAC inhibitor, we need to have a kinase binder, an E3 binder, and the proper linker to connect those two. Now, kinase binders, it can be kinase inhibitor or just a binder to the kinase. It doesn't need to have any functional inhibition to the kinase. Just the physical binding is all we need. E3 binder, there are many kinds of E3s, so we can choose different kind of binders here. Now, one important issue here is the size of the molecule. Maybe kinase binder, small molecule, molecular weight is 500, And E3 binder may be another small molecule, maybe molecular weight is around 500. Now, if these two molecules combined together, the total molecular weight is near to 1000. So that's not small molecule anymore. So it may have a serious pharmacokinetic the property issues. That's why to make this linker shorter and shorter, and then binding site both for the kinase and E3 site, make it simpler and simpler. Eventually combine this molecule together, almost one molecule and small size. And if that can be achieved, that kind of molecule is called as molecular glue, which is one big trend to develop these molecules into practical drugs.